Okay, we are back, and I fixed the sound. I'm playing about with a drawing tablet. What pen are you? Fine line pen. Ah, yeah, you'll do for a bit. Um, which is cool. I'm liking this thing. A little bit smaller. That's probably a little bit too small. It's still too small. And let's go up in opacity a bit. I don't really know what I'm doing. Change type. Oh, wow. No. Shan't be doing that. Okay, now we have an actual line. Anyway, we're going to do some more network calculus. I'm excited to try it. Whoa, 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 whoa. Why are you so thick? Oh, this is the fine line. Okay. I'm excited to try doing someone here. So, if you're just tuning in, this is a little series I've been doing where the last few, if you're interested at all, you can go back. I'm collecting them together, a playlist on YouTube. The last few episodes I've done, I don't know what to call it, have been setting out, like, basically what I had when I stopped thinking about this last. So this is the third time, like, there are more than 3 episodes, but kind of the third day of thinking about it. Let me just grab what I had before and translate a bit of it to this. Can I do pages on this, do we know? Guess I could do it as layers. That's not how you're supposed to use layers, but let's do it that way. So, this is about translating the actions of a network to a kind of programmable algebra. So just as a reminder of how we're doing this, we've got... Oh, that is not vertical. Why am I so off? We have... Verticality is surprisingly hard when you're moving the pad around. At each layer, we have some inputs that are passed. Can I get like a nice soft? No, I don't like that. Ooh. I have a button for zoom in, but I don't apparently have a button for zoom out. How can I move? The good old zoom out one direction, zoom back in the other. No, oh god, I'm doing all kinds of things. You know what, that's fine. So we have inputs that are then being passed by some weights. Okay. Sometimes I'm drawing the arrows on these, sometimes I'm not. I'm trying to develop kind of semi-consistent language. They can be passed to multiple places. They can also be passed with like positive signs and negative signs. This is how I'm drawing positive and negative signs. This means positive 1, negative 1. The other piece of nomenclature that I've been using a bit is lambda is positive much less than 1 and is used as a kind of general, if we multiply something by lambda, it's now a small number. this is multiplying through by +1. This is multiplying through by -1. Then we pass the weighted sum of these into some function. And for the moment, we've been saying that everything is the same function. We're going to actually... I'm trying to think of a good visual language for this. We're going to start relaxing that a bit. Let's call this function theta. This function. No, did it wrong again. I'm going to start drawing these ones like this. I'll try and be really clear about this. When you see soft edges, well, we'll see as we go. I'm going to call this one phi. So these are our... I'm going to get rid of these, a bit much to have now. These are our activation functions. Activation is not that useful a word, so we're just going to call them our functions. And then they output always a single number, and we have our outputs. So our outputs are right now theta. They also have associated with them a weight. So just like these have a k. I don't have a good way of writing this. Maybe I'll put it like here. Underneath. Seems fine. Bottom left. Seems fine. So they will always be theta of the inputs multiplied by their weights minus the bias. So here we have A minus B minus the bias. So right now we've kind of assumed that these functions are a single function, single monotonic function. So that might be something like we're getting the habit of changing pen color more often. How do I even do that? Luminance, saturation. Yeah, seems fine. So it might be something like the swish, which is sigma. Let's call this Z again for the moment. Is Z over 1 plus e to the minus z. Is that legible? Yeah, basically is. The system works. They also might be something, so this goes off to infinity. Vertical lines are going to be hard with this. They also could be something like, how do I get back to that blue? Fine, this is grey. We're just gonna, everything's grayscale now. They also could be something like a sigmoid, which is actually just, so that tops out at 1, and that is phi equals just 1 plus e to the minus z. So this is what, I'm going to do this very light shading again over this. Not in love with that way of shading, but it will do for now. This is one, or at least one, layer of a network. And these networks, they might start with some true, one or two true inputs, A and B, and then just to kind of repeat this architecture, I'm not going to draw the weights on these. We're giving these to two functions. But that might just be the first step. We could then pass these values on. So we haven't really defined what these values are, but we could pass these values on to another few functions that are doing other kinds of work. And we could even have things like, you can have a recursive loop, which does something like that. Let's put arrows on all of these. They're all feeding forwards. And then eventually you get some number out. And we want that number to be meaningful. Like maybe the number we want out is the final output is if A over B is an integer, return its. Sorry, internet, I can't ever work out what I'm meant to be doing. Return its value, else return 0. So with these simple operations, we want to build up to a we're going to put in simple inputs, but potentially lots of them. We're going to put them through lots of simple functions, and they're all going to be this weighted sum of the function with some bias. That's the only structure we're going to use. And we'll get, hopefully, few complex, or let's not call them complex. Let's call them useful. I mean, that's the point of this, isn't it? We want something useful. Few useful outputs. So that's, do I have like a highlighter? Everything is grayscale. Whoa, that's not what I wanted. Oh gosh. Even that's a bit much. Because I actually want the opacity to be down, so let's go back. That's not what I'm doing. Whoa, no. No, don't go down here. So putting in lots of simple outputs to get through lots of simple functions and trying to get out a few useful outputs. So let's said earlier I didn't know how to do this. Well, I'm going to do it by just adding new layers each time. So at least this way I can go back to things that already existed. Why? Because I'm not in this layer. There we go. So just to be a bit more concrete about some of the language I'm using, square box, well, let's just look back at this rather than me drawing it out again. Square box is always a swish for now on. We're going to assume it's always this form when it's a square box, and actually we're going to put alpha in the box. Curved side box is always going to be a sigmoid, and we're going to put beta in the box. So let's take the time to map that out really clearly. No, that's clear enough. Let's start making some functions. So I'm going to write out some of the ones that we've already walked through. I think I've shown you these a few times now. But I don't think this is very easy. So I think it's worth doing it a few times. The first function that we care about is the identity, which is also the addition function. So this takes A, it's a 1-1 function, and it maps it back to A. I'm still 50-50 on whether or not to bother drawing. Woo. Whether or not to bother drawing the verticals on these, but let's for the moment. And it also takes A and B. It kind of is the subtraction function as well. And maps it onto A plus B. It can take A, give A negative weight, and it will give you back minus A, and therefore it can take A and B, give A a positive weight, give B a negative weight, and it will give you back A minus B. So it's a useful function, does a lot. But like, what is the function inside this? Because even this is compressing some information down. So this +1,1 function actually looks like this. Gamma. Put it with sigmoid 0, and pull it back with 1 over lambda gamma 1. So what do all these terms mean? Well, remember this says that there's a number gamma is greater than 0. No, that's not the way you do that. So lambda is greater than 0, but much less than 1. Let's put a box around this, because this is our first first definition that we'll start using. So why does this work? Well, the function in a box, remember the box of alpha is equivalent to applying the swish. So the swish looks like, if I actually look at my hands, it's much easier to draw straight lines. Maybe that's obvious. So sigma z minus alpha z and alpha. This looks like this. So now you're kind of seeing what the alpha does. The alpha shifts it one way or another. And the full definition is that this is the sum of all of the weights of the things coming in and all of the values of the things coming in, minus alpha. So in this case, the only thing coming in is a small number, a, times this very small number. So in this case, we've got that it's sigma of lambda a minus alpha is 0, so it's just sigma of lambda a. So sigma is this is lambda a over 1 plus e to the minus lambda a from our definition of theta. Again, if you're watching this, I'm sorry, I'm all over the place on what I call different Greek letters. But these are small. That's kind of the whole point. So e to the minus a is roughly 1 minus lambda a. Let me just, in case anyone's looking at that being like, that's a little bit suspicious. I'm hoping someone's made a nice interactive, no. Maybe. Okay, so here we're talking about y equals e to the x, and so e to the x is just goes through 1, but if we add in a linear term, that linear term is e to the x plus x, and it's actually, if we zoom in, which we're not allowed to do, I probably should just do this on Wolfram Alpha, shouldn't I? Oh, here we go. So this is showing in blue the curve we're actually approximating to, which is e to the x, and in red our approximation. And starts out as a flat line because it's just a constant, and that's not a very good approximation. But even the first step, where it's just a straight line, is actually pretty accurate for a lot of this this region between like -1 and 1. Put in like the third order term and it's accurate pretty much the whole way to -2 to 2. And as you go to higher and higher terms, it's accurate for longer, or it's more accurate, depending on which way you think about it. But for x is very small, in this tiny region that is actually quite hard to see, is very accurate. In fact, it maps onto the true value. This is something that you learn in university mathematics, maybe even like A-level, maybe even GCSE. but can feel like, why am I doing this at the time? Mapping complex functions onto simpler ones. And the reason is because it actually makes calculations easier, because this is roughly equal to this. So, okay, great, that's small. So 1 over this is roughly equal to, a way of putting this is that all the extra error is proportional to this squared. So this is tiny because lambda is very small. So this squared is tinier still, doesn't matter. So this is the same as 1, in fact 2 minus lambda a to the minus 1 plus those second order terms. And this, again, Taylor expanding, is half 1 plus lambda a over 2. So that means keeping only the things first order terms, that lambda a times this is actually just lambda a over 2. Sweet. The higher order terms would then give you a, yeah, no, that's right. Give you a lambda squared a squared over 4, and then higher order terms still. So when we put this, when we apply this function to lambda a, we get out lambda a over 2. So to get a back, we now know what gamma 1 is. Gamma 1 is the first order bit of the expansion, so I've been rough on that. Again, if you're watching this, this is very much first draft of something that one day might be a lecture. Lambda 1, is that right? Is that the pen I'm using? No, that's the pen I'm using. Lambda 1 is 2. So actually we know that we're just going to multiply through by 2 here. And we'll have got back our original answer. So, great. We have the ability to add and subtract numbers. Woo, go us. Let's add another layer. Okay. Wait, I just want to make sure. I like to repeat myself. Apologies if anyone's watching the whole thing and they're like, you told us this twice. I find repeating myself helps me make sure I got all the details, and you're watching these on a medium where you can skip and pause and move around. Except for the poor one sap who's watching live. Ain't nothing they can do. So, now we want to make a more complex operation. We want to make something that takes A and B and multiplies them together such to get out AB. And what we'll actually find as we do this is that this is a more complex network we have to make. And I'm just going to draw it out. What is this? Let's put it over here. So this is our end goal. So this thing, I know I haven't explained these numbers, they will come in as we go. a multiplication operator is equivalent to it's taking this actually only right now can multiply two numbers, so maybe it should have that in its form. Well, let's not worry about it too much. It's taking two numbers, it's splitting those off, a positive, a negative, negative, and a positive, and then this one, which I haven't got any space for, is going, let's draw it in a different colour. Is going up here. I'm also going to try and not cross the lines too much. That's barely a different colour, is it? Nice bright blue. I also want another positive. Both of these positives. Again, try not to cross the lines. Positive, and then these guys are negatives. I had a good way of drawing this before. This is, amongst other things, a new notation that I'm putting together here. So sometimes it will be pretty scruffy. Yeah, here we go. This is much nicer. Let's take the time to do it properly. I'm going to do it all in one pen colour, because I think if you have maths that needs to be written in two pen colours, you slightly reduce the number of people who are actually going to learn it. So it's taking in two inputs. Stick with black. You know what you are with black.
110.
110, great. So we've got these two inputs coming in. We can see it's splitting off a positive and a negative from each of those two inputs. Positive. You might notice that what I'm drawing here looks not unlike a circuit diagram, and there is a lot of similarities there. And I want the positive going to here and to here. I want the positives from here going to here and to here. Let's actually have that going a bit further along before it splits off. And the negatives, looking at this, just connecting everything else up, must go to here and to here. And the negatives must go to here and to here. One of those lines is really messy. So if this is A and B, then we have up here A plus B, B minus A minus B, minus A minus B. We haven't passed these through a function yet, so all we've done is just some arithmetic. And we can do all these arithmetic steps as many times as we want. We always have to pass things through a function. I talked about that in the last video. If that's, for the moment, trust me on that. Now we're going to pass these through a function that looks like I'm going to put in a lambda to each one. Remember, this is just the number that makes everything small. And we're going to pass these through our nice friend, the swish. 4 different swishes. And then so actually this just has to be not 0. No, wait, is that true? So with the switch, these numbers will vary a bit. I'm constantly going back and forth on like how general versus how clear I want to be. I think we can pass this through 0 here. Yeah. Pretty sure we can. We'll find out if we can't as we go. So I'm then going to go straight. I'm not going to even draw the outputs of this because for one thing I don't have that much space, and send these all into one addition operator. And before I do that, I'm going to have to divide by this, and we'll divide this factor later, but this applies to all of them. So actually when it applies to all of them, let's just write it at the top. And we get out A times B. Now, I think I said this last time, but this isn't my... This was the thing that inspired me to start thinking about this, seeing this at work, because it's both, it's pretty complex, but it's also not too bad. Oh, and maybe I should point out why is this called a 412? I don't think I even need the 2. You know what, I'm going to keep the 2, but the 2 is going to be the number of inputs it wants. No, then it should probably be on the other side. I think the 2 is obvious. It wants 2 inputs. Maybe it should... Yeah, maybe it should have this on either side, 2 inputs to 1 output. That's not a bad convention. Let's start thinking about... what if I wrote it? Like this, so the thing on the bottom is the input number, output number. The full 1 here refers to the number of nodes needed in each layer. So we've got to go through 1 layer of 4 and then 1 layer of just 1, because we know that the plus operator is just a 1. It's just 1, and it goes from, you can have any number of inputs and it gives a single output. So I'm going to say that's 0. I think that makes sense to say it's 0. So let's go back and in this language look at our plus operator from before. Which we're going to I guess it could have all these on this side. Maybe I want that instead. So it's just a 1. What if I made it this way round? The top was the inputs it's taking, and it's just a 1. I like that. Okay, that's how we're doing it now. No, that has an issue, which is that this top bit might get really long at some point. But the side bit is always going to be 2 numbers. Seems fine. 0-1. It's become a kind of divisor. Feels fine. Okay, now in that language, what does our thing here look like? Actually, that's really not bad, is it? That's quite handsome. If I draw a plus in this. And I like the fact that this looks like a flow. I'm gonna go eat lunch in a sec, so I haven't really got anywhere with this today. 1, 0 to 1. Yeah, I think that's pretty good. Let's keep it like that. Just got to draw it in the right order. You've always got to think about what's something that I'd be willing to draw enough times. Now, you probably don't need to draw all this every time you draw one of these. It's just you tend to make conventions that are watertight and then relax them until they're kind of clear, but you don't actually need to be that explicit about them. Okay, so we have successfully finally settled on maybe a convention for the moment, because I'm realizing that it is important to include whether number of inputs and outputs, because we just lost layers. Can we get layers back? There we go. Whoa! No, please go away. This is how we were able to draw over here. There we go. I know what you are. this wouldn't work with more than 2 inputs. I guess I could be numbering the number of connections needed as well. This possibly should be called network architecture, not network calculus. I'm going to go have lunch. When I come back, we'll probably talk a little bit about how this works and find this value of gamma 2. And in fact, I will even define what gamma 2 is, but before I go, just to leave you with a thought, what I mean by this is that when we have, when the input is small, then this can be seen as a Taylor expansion. And we could keep going, but this will be enough now. And it's this that we're representing as gamma 0 plus epsilon gamma 1 plus. We'll keep the 2's because then this means that gamma n, which is actually a function of alpha, is d to the n theta over dz, d to the n of theta z over dz, evaluated at alpha. Should use a different colour for these boxes, shouldn't I? So, if you were so inclined, while I'm away having lunch, see if you can work out for yourself why this gives. No, wrong one. Why this works, and what the value of gamma 2 is. And I will see you in a little bit. Well, no, I won't, but you might see me. The opt-in panopticon continues.